pH is another factor that can dramatically alter the solubility of a particular compound. If when you have a compound and you dissolve it in a solvent, let's say water, the anion of that ionic compound is the conjugate base of a weak acid, that means it's a strong conjugate base, and it will react with the hydrogen ion. So the salts of weak acids tend to be more soluble in acidic solutions because the conjugate base is strong, and it will react with the hydrogen ions, and that will help displace the solubility towards the formation of more ions. So if we look back at the example of calcium oxalate, when you dissolve calcium oxalate, you form calcium 2 plus ions and oxalate anions. And oxalates are the conjugate bases to the oxalic acid or the hydrogen oxalate, which is a weak acid. That means that they are strong conjugate bases. So in the presence of hydrogen ions, you have a reaction, another equilibrium being established, in which you form the hydrogen oxalate anion. So increasing the concentration of hydrogen ions, decreasing the pH, making it more acidic, means that the equilibrium is displaced to the formation of the hydrogen oxalate. Therefore, the reaction is displaced towards the dissolution of the original calcium oxalate compound. Another interesting fact to take into account when thinking about solubility of compounds of ionic salts, inorganic salts, is the formation of complex ions. The metal ion, the complex ions is formed, as we studied in previous topics, when you have a metal ion and a ligand, and it's a Lewis acid-base interaction. The metal ion is positively charged, it acts as a Lewis acid, and the ligand that has either a negative charge or a lone pair of electrons acts as a Lewis base. An equilibrium is established between the insoluble salt, the ions in solution, and the potential of those ions in solution to form complex ions. And all that is called the complex ions formation. And I'm suggesting here that you watch a little bit, maybe 1 or 2 minutes short, what happens when you add sodium hydroxide to a solution of chromium 3 nitrate. So what happens is that when you have the solution of chromium 3 nitrates, you have chromium 3 dissolved in water. Adding sufficient amount of sodium hydroxide produces the precipitation of chromium hydroxide, chromium 3 hydroxide. However, if you continue adding hydroxyl ions, if you continue increasing the pH, the chromium hydroxide redissolves to form the chromium 3 hydroxide, hexahydroxide anion. So here we see an example in which how an ion, which is in solution, by adding a particular ligand, in this case the hydroxyl ion, you can form first the precipitate, the solid, and then redissolve that precipitate, again to form another ion, but a different one, with hydroxyl groups surrounding the metal ion, rather than the water molecules. So a different ion to the one you started with. So this equilibrium between the formation of a complex ion from a hydrated ion, so the ion surrounded by molecules of water and the ion surrounded by molecules of a ligand, is determined by what we call the formation constant, Kf. And here we have an example of a hydrated copper 2 plus dissolving water, so in aqueous form, hydrated, the copper ion 2 2 plus hydrated, and in the presence of ammonia, sufficient quantities of ammonia, a complex ion with 4 molecules of ammonia is formed, and that has a formation constant which can be defined as, in a typical equilibrium constant, the concentration of the product to the coefficient, to the power of the coefficient, divided by the concentration, the product of the concentration of the reagents, again to the powers of their respective coefficients. The dissociation constant for a complex will be the reciprocal of the formation. So if you look at the reaction this way, then you're looking at the formation reaction. So you're looking at the formation constant. And if you're looking at the reaction going the other way, from the complex to the original ions, to the original ligand and metal ion, then you have dissociation constant, and they are reciprocal from each other. If a complex ion has a large formation constant, that means the reaction going forward to the formation of the ions of that complex ion is very favorable, then that can dramatically increase the solubility of that ion when it's in a formed salt. So by forming that complex ion, it's possible to move that metal ion in solution, and that helps aids the solubility for highly insoluble salts. Typically, these formation constants are looked at, are measured and presented sequentially. So if we go back to our previous reaction, the hydrated copper ions, copper 2 ions, and mixing them with ammonia molecules to form the ammonia complex of copper 2, you can define 4 formation constants for this complex, and it is the subsequent removal of a molecule of water from the coordination sphere of the copper, and the addition or the substitution for a molecule of ammonia. So the copper losing 1 molecule of water and getting in the coordination sphere 1 molecule of ammonia, the copper losing another molecule of water, and yet another, until you form the final, the final complex with the 4 ammonia molecules in the coordination sphere of the copper, and the water that was originally there in the coordination sphere having been displaced by the ammonia molecules. And what would be the formation constant for the overall reaction? Well, it would be the product of all these sequential formation constants.